Welcome to this lecture on metric spaces. Today, we are going to explore a fundamental and highly visual concept called the diameter of a set. By the end of this video, you will understand exactly how mathematicians measure the absolute maximum spread of any collection of points and why this idea is so crucial in both pure mathematics and real-world applications. Let us start with an intuitive picture. Imagine a large flock of sheep grazing in a wide open meadow. If you wanted to measure the overall size or spread of this flock, you would not weigh the sheep or count their legs. Instead, you would look for the two specific sheep that are standing the absolute furthest apart from each other. You would take a long measuring tape and measure the straight line distance between those two specific sheep. That longest possible distance gives you the diameter of the flock. In mathematics, we do the exact same thing with sets of points to understand how spread out they are. Now that we have an intuitive idea, let us translate this into the formal language of metric spaces. A metric space is simply a collection of points equipped with a specific mathematical rule for measuring distances between any two points. To find the diameter of a subset, we calculate the distance between every single pair of points inside it. We then collect all these distance values into a massive new set of numbers. The diameter is formally defined as the supremum of this set of distance numbers. The supremum is just a formal mathematical term for the least upper bound, which acts like a maximum limit. This brings us to the formal mathematical equation for the diameter, which captures exactly what we just discussed. The symbol delta of A represents the diameter of our chosen subset A. The symbol sup stands for supremum, meaning we are looking for the smallest number that is greater than or equal to all the distances in our collection. The expression d of x, y represents the distance between 2 points, x and y, according to the rules of our specific metric space. The vertical bar means such that, ensuring both points are chosen strictly from inside our subset A. Also, if the set is completely empty, mathematicians universally agree to define its diameter as 0 because there are no distances to measure. Before we move on to a numerical example, let us see this visually. The diagram on your screen summarizes the formula we just discussed. You can see a set of points labeled A. There are many possible distances between these points, which are represented by the grey dashed lines. However, only the absolute longest span matters for our calculation. That longest red line represents the supremum of all those possible distances. This single measurement tells us the maximum possible spread we could encounter if we were working within this specific set of points. Now that we understand the formula and its visual meaning, let us look at a concrete numerical example. We want to find the diameter of the closed interval from 2 to 8 on the standard real number line. The closed brackets mean the numbers 2 and 8 are included in the set. We will use the standard distance metric for real numbers, which calculates the positive gap between any two numbers using absolute value bars. We substitute this into our formula, meaning we are looking for the supremum of the absolute difference between any two numbers chosen from between 2 and 8 inclusive. Continuing with our calculation, we need to find the largest possible gap. To get this maximum distance, we should pick the two numbers that are furthest apart. Naturally, these are the extreme endpoints of our interval, which are exactly 8 and 2. We substitute these specific endpoint values into our absolute value distance formula. This gives us the simple arithmetic difference between the two extremes, which is 6. Therefore, the diameter of this closed interval is exactly 6. This makes perfect physical sense, just like a stick lying on a ruler from the 2-inch mark to the 8-inch mark is exactly 6 inches long. Let us tackle a slightly more complex scenario. We will find the diameter of the open interval from 0 to 5. An open interval includes all numbers between 0 and 5, but it strictly excludes the endpoints 0 and 5 themselves. This is exactly why the formal definition uses the word supremum instead of maximum. We cannot just pick 0 and 5 to measure the distance because they do not actually exist inside the set. We must look for the least upper bound of all distances between points strictly greater than 0 and strictly less than 5. Since we cannot use the endpoints directly, we must look at the behavior of the distances as we get closer and closer to the edges. We can choose points that get incredibly close to 5, such as 4.999, and points incredibly close to 0, such as 0.001. The distance between them is 4.998. If we pick points even closer to the missing endpoints, like 4.9999 and 0.0001, the gap increases to 4.9998. We are pushing the points as far apart as the boundaries will physically allow. As we continue this process, the distance between the points gets closer and closer to the absolute limit of 5. We can get as close to 5 as we want without ever actually reaching it, simply by adding more decimal places to our chosen numbers. Even though the exact distance of 5 is never actually achieved by any two specific points inside the open interval, the distances get infinitely close to it. Therefore, 5 is the supremum, or the least upper bound of all possible distances. This perfectly illustrates why the formal definition uses a supremum instead of a simple maximum. Now that we have calculated diameters, you might ask, why do we care about this? In mathematics and physics, we constantly need to know if a system is bounded or if it can blow up to infinity. A set is officially called bounded if and only if its diameter is a finite number. For example, in engineering, if you are calculating the possible errors in a sensor's readings, the set of all possible errors must have a finite diameter. Otherwise, your system is completely unstable. In computer science, clustering algorithms rely on keeping the diameter of each data cluster as small as possible. Let us review the key takeaways from today's lecture. We learned that the diameter of a set acts as a mathematical measuring tape that finds the absolute widest span of a collection of items. Formally, it is the supremum of the distances between all possible pairs of points within that set. Using the supremum is incredibly powerful because it allows us to find the diameter of open intervals where an exact maximum distance is never reached. Finally, we saw that if this diameter is a finite number, the set is safely bounded and contained. You now have a solid understanding of the diameter of a set.